Hi everyone. As you know, my name is Bipin Babu, and I'm working as a KDP associate with University of Stirling and Keep Scotland Beautiful. Today we are here to discuss about our project on AI-driven real-time state data detection. A 2 years project that we are running in partnership with University of Stirling and Innovate UK. Um, Second, what's going on? So a bit introduction about me. So for my, as I said, I'm Bipin and I'm working as an AI engineer, KTP associate with KSB. Um, and before this, I used to I am an alumni of University of Stirling from 2023, 2020, to 2023 batch. I also used to work as a teaching assistant here right after my graduation. Um, and before this, I used to work as an AI prompt engineer and data analyst at Itza Media. It's in Edinburgh where I used to make chatbots for students from across the globe to help them study and facilitate their learning. And I also used to work as a program analyst in India before joining Itza and University of Stirling. So yeah, that's a bit of our background about me. On to the agenda. So, what are we going to cover here? So, a bit about litter pollution, what it is, and what are we trying to solve. KSB's initiative. So, I'm going to refer KSB as Keeps Growing Beautiful. So, just for your reference. And also on the model explorations, what different models that we have checked out, some challenges that we have encountered on the way. Also the current methodology, like what are we trying to do, how are we approaching the problem, and also some takeaways, some pilot program discussions that we are currently having, and the deployment of the important part of this project. And finally, any questions that you have, happy to answer. So, talking about what are we trying to solve? I think it's clear from the image. You can see there is a massive litter pollution that's emerging in Scotland, and not just in Scotland, across the world. It is everywhere in the UK. It's outside the UK, but right now in Scotland, it's a big problem, and we need to tackle that. And there was a survey that was conducted by Diffley in partnership with KSP this month. And out of the survey, 66% of the people agreed that they are embarrassed by the neighborhood because of the litter. And there is also a survey that conducted said 64% believe there is an antisocial behavior that's being emerged because of this, and the psychology of the people changing because of the litter present in their neighborhood. So that's a pressing issue. And considering all of this, um, KSB has decided to tackle it in a different way. So right now, what they're doing is the volunteers or the KSB officials go onto the street and do the auditing, and they take pictures of the litter. So they say there are 25 cigarette butts or two McDonald's packets and so on. So which is very tedious and manual work, and it takes a lot of time, and you can't visit all the streets in Scotland and like that. So there should be an efficient way to handle this, and that's when KSP started thinking about how we can use artificial intelligence to tackle this problem, and they came up with this project. And the initial aim that I was assigned to was develop a smart camera or make the camera smart such that it can be attached to a truck like this, and so that when it goes across the street, you can collect the data of the litter, so you don't have to be on the street just for data collection. It will automatically be done by the vehicle. The second idea was to infer the litter detection from the dash cams, because most of the cars have dash cams these days, so you can just collect the data when you're driving. The idea seems simple, but it is very complex in reality, because if you attach a camera like that on the side, there are many parked cars on the side of the road, and that obscures the actual litter. That's one issue. And also the speed of the vehicle is another issue. And from a distance, all the litter might look alike. So it's very difficult to actually sort it out. And also the small litter bits like smoking litter or chewing gums is very difficult to identify from moving vehicle. It is doable, but not when there are no product for TSB to sell. So you can't add this functionality initially in this 2 year span of time. So we slightly pivoted from this idea on to something that's doable right now, which is, of course, a detection for mobile camera because it has GPS, it has a GPU, most of the smartphones these days, so it can run models offline. And we are also privacy centered. So that's I'll come to that in a later slide because privacy is very important when it comes to AI, responsible AI, and so on. So we decided to build our own KSB's official app, and that's focusing just on data collection. And it's also restricted not to the general public, but to the local authorities. So that's the idea, and we decided to move on with this approach. So the first step in that is to figure out or come up with the litter categories. So, and there are several litter in this country, but we need to categorize sort them into something that's meaningful to the local authorities. So after having several discussions with local authorities back and forth, we devised these categories. So smoking litter, rinse litter, pool litter, hazardous items like blade or batteries. Then comes the personal hygiene stuff like masks, dog litter, refuse. So refuse is like bins or something that's dumped on the side of the road, like an open case. And unknown litter, like let's just take many a time we don't know what we are seeing. It can be ages old litter, but it can look like something else because sometimes bird poo can look like chewing gums or a twig can look like maybe smoking litter. So it's very difficult. So we need to add another category called unknown litter to capture everything that's we are seeing. So if the labeling team is not sure of what category it belongs to, they will tag it as unknown. So that's how we approach this problem. Um, and in order to detect, we came up with a simple architecture initially. So this is just the vague architecture. I am not able to provide the in and out details because of the IP issues. But basically, what we're trying to do is you give an input image, you find the high level literature category, maybe run a good detection model and do that, and then we'll crop it out, whatever object you're seeing, and then you pass it to another model to get the material, whether it is a rubber or plastic, and also you can get the data by item, whether it is a plastic cup or if it's a straw that you're seeing or and the item by itself. And all of this can be combined with.
No, I think you just remove it. Because if you press that, yeah.
Oh, it's mixed. So you can also combine this with the brand information, like whether it's a McDonald's packet or if it's a KFC or if it's Greg's. So you can get that, and also you can get the dimensions and weight of the litter as well. So that's another important part of this architecture. It's very scalable and it's very doable as well for an initial version for a product that needs to be commercialized. And everything that we have identified needs to be combined in a way that's presentable to the audience, like for the non-technical people. So that's where we do that, and we will sync everything on the cloud when the internet becomes available. And that is done because at the end of the year there will be auditing happening. So the councils have to show like as proof that these were the litter that we have found, and we need to collect the evidence images as well, which is also a key part of this project. Um, so talking about the first stage of how we approach this problem is data collection. Just like any other machine learning or AI projects, we need a lot of good quality data. So KSB already had some existing database of images because they were working with environmental problems. But we relied very less on that because the dataset wasn't suitable for our project primarily. Because if you remember, we were talking about the mobile app. So the mobile app is like and you take the app and you walk around to record the pictures, and the angle is quite different from a close-up image of a litter. So the dataset that they had were not suitable for our problem, although to an extent it is. So we had very minimum reliance on it. So we started actually collecting data for this project using mobile app from Stirling Glass and also we have partnership with Keep Waste ID. So we started collecting data from Wales as well. And we have 3-member labeling team starting and doing all the annotations. Very few number, but we are still managing to do the labeling faster. And we used an open source tool called Label Studio to do this, which you can find here. And these are some of the sample images and how it looks like. There's also a picture from the dash cam because we wanted to train the model on dash cam images as well. But that's not being done right now. That's how usually the images look like. And so the team will go out there, capture the video, then we extract images and feed it to the model and runs continuously. And then comes the model exploration part. So you might already know what YOLO family of algorithms are, like the single pass detection and one of the state of the art model, very good performance. And that video that you see there are from YOLO with just 500 images. It was able to detect all the letter categories with more than 70% precision. And that's like really remarkable. And we also tried faster CNN, but faster CNN was not giving much results because of the lack of data, enough data. But YOLO was really good at it. And however, we found YOLO had this licensing issue, which they belongs to the Ultralytics company, and they have this AGPL license, general public license, where you have to open source your backend if you were to commercialize it. So that's not good if you are IPing it. So you don't want to give away your code to your competitors. There are a lot of competitors in this market space. So we had to look for other options. Pastoral scene is definitely an option, but we wanted something strong to capture all the glitter and with the same performance as YOLO. So we started looking for other alternatives. And that's when we started looking for things like RT-Deter. Are you familiar with RT-Deter, anyone? So deters are called as detection transformers. If you know transformers in language models, it has the encoder, decoder, and the attention mechanism to make sense of the tokens. So the same thing, if you take it to computer vision, we can use the attention, the power of attention, and to predict the objects without going through the non-maximum suppression or other post-processing techniques and faster processing and any other algorithms. So very good. So in 2020, this is not the one. Deter was released. So Deter is like detection transformer, the basic one from by Facebook, and that was like a wave in the object detection like domain. But it was way too slow because of the attention and encoder or decoder. It was not good for real-time detection. And in 2024, real-time detection transformers came and they are used for detection in real time from other devices. So we used this and we were able to get not good as Europe, but comparatively better performance. And then we tried something called Define, but it was just a waste of time because there had some issues on the GitHub and we couldn't run this at all. So we had to dish that. But finally, we found the best model out there right now, which is the RoboFlow detection transformer. Very fast, and this came at the right time. It had performance better than YOLO. YOLO 11 large model. So it was like completely open source, and it was like a gift given to the open source community. And we got good results out of it. So you can see here the detections are quite like you had with YOLO, and it's a video from Stirling. You can see the model running. And you can see that it's even picking up the bin that's far away from the user. Excuse me. So that's the all the models that we have tried out and tested, and out of this, RoboFlow is the best till now, and its performance is comparable to Europe. Maybe I would say even better than that. And we have full control of the code because you can update the weights, you can do anything you want because it's fully available to you, unlike the Ultralytics package. And if you need to train this, you need a good resource. So fortunately, we had this tie up with Hartree Center. So KSB got a license funding. So we were able to use their machines of 64 gigs of GPU to run this. We didn't use 30% of it, but not even 30% of it, but we were able to run this quite well compared to the university GPUs. So yeah. And then comes the most important part, like I discussed before, privacy, because you're on the street, you're recording people, you're recording other sensitive information like license number, and you don't want your information to be tagged to some third party organization. So you need to handle that. So how are we handling it? We can mask the face, we can mask the vehicle registration number, and we have to do this before we give control to the user who operates the app. So that's when we started looking for open source tools to do that, and we found the ego blur model, which is also built on top of Saracen convolutional neural networks by Facebook research, and we implemented this model to mask all the sensitive information from a given image. So you can see sample here. There's a lady at her home, and we were collecting data. Unfortunately, she fell into our data set. So we had to mask it, and you can see after running the model, the information is blurred out and there's no way we can identify her. So that's removed from the same works for the license plate number as well. And the difference is speed is also like 2 seconds, even less than that. So very light model. And also the next question is how do we feed this to non-technical people? How do we make sense of what we have captured? So that's when a web dashboard is very important. So we need to work on a web dashboard to communicate the data well. So we need to integrate a map like that. So this is not a prototype, it's just a demonstration of how it might look like once we have done. So there will be a map and you can see the literal density, and you'll be having the option to make sense out of the data, or even the data collection that you have done in the past, or if there is any hotspots, little hotspots that's emerging, that you can use machine learning or something to make sense of what you're doing. So that's also being done. And this is, we might start January, February next year on the development of this once you've completed the app. And also the edge deployment. So this is just like I said, privacy focused. And imagine you capture 20 videos a day. We can't send all of this to the cloud because that will take a lot of bandwidth, and that's not the efficient way to do this. So we need to deploy the models at the edge, and also we need to make sure it can be even utilized even if there is no internet connection. So that's the another thing. So in order for the models to run offline, you have to optimize it. You have to optimize it really well that even 4 seconds reduction to 2 seconds during inference time is a lot of difference. Because in our case, if 2, 3 models are speaking to each other and each model takes 4 seconds, that's 16 seconds in total, and that's a lot of time for each video. So each frame. So you have to cut it down to as much as small as we can. So yeah, that's the another challenge that we have to deal with while considering edge deployment. So I just wanted to touch on some optimization techniques that we can usually try when we deploy online, so or offline. One of the techniques that you might be aware of is quantization. So it's basically converting large numbers into something small, like a floating point 64 to 32. It will obviously affect your precision, but if you can find that balance, the model will be faster and the precision will be a trade-off. And then comes the pruning. It's just like the pruning in botany, where you cut off the unwanted neurons or weighting in order to make the model light and increase the inference speed. And also the knowledge distillation part, which you might know. So we train a smaller, lighter model to mimic a larger model. So you don't need the larger model in a sense. We can run the small model, but in many cases it's very difficult to achieve the same precision as a teacher, but it can also work. And also, one of the basic thing that we can do is whenever we select a state of the art, always go with the lighter versions. For example, YOLO. If you're selecting YOLO, there is a large, medium, and a small. So if you pick the small and then work on it, then it might be much faster compared to the larger model. So in our case, we always pick the small models to make sure it run effectively at the edge. So yeah, these are the some of the optimization techniques that we can try. And there are more, but yeah, some of them. Yeah, and this is the app that how it might look like. So right now we had an intern from Sterling building this app for us. So all the UI is done. The 40% that's remaining is the integration of the model onto the app. So we use PyTorch mobile for that. And once we integrate it, so the models will start communicating to each other all offline. And then we will test this app for deployment. And comes to the challenges, just like any project, we had a lot of challenges. And that's the interesting part because if you have challenges, you will learn and then you will also find new way to solve this. One of the issues that we had was EXIF orientation. Are you familiar with EXIF metadata? So whenever you capture an image, like it has a metadata associated with it, like latitude, longitude, the location information, the time, and also orientation and so on. So the orientation is the actual culprit, was the actual culprit for us because the images captured were usually from different smartphones and all of them had a metadata along with it. Like we need, so the orientation tells the device that the image is shown, that you need to rotate it 20 degree or 30 degree in order to view it upright. But not many Python libraries respect that information. For example, OpenCV doesn't respect EXIF. So you might think you are feeding the right image to the model, but you are not. You can see here, um, the bounding boxes are like scattered. It's not at the right location. So this is one of the things that was slowing down our progress because because the image might look, if you rotate the image, the bounding box will come to the right place, but if not, it will be scattered. Because in if you use an open source tool like Label Studio, they respect this orientation and it will show you upright. Then you put the bounding box and you save, but they are actually saving not on the upright image, but on the rotated image, and that causes a confusion when we load it into the model pipeline. So we have to use the Python imaging library, clear the EXIF orientation tag, clean all the images before feeding into the pipeline. And the next issue was the faraway litter, because like I said, a paper and a tissue paper might make the light. So
Sorry.
So that was one issue to deal with litter that are far away and blurry. We are still struggling with that, but as the person move closer to the litter, like if we can remove the duplication, we can solve that problem. So that's something that we are currently experimenting with. Like I said, the model licensing, the GPL license had, so in academia, it's not an issue because for academic purposes, you can use YOLO, you can use any model under the general public license, it's fine. But if you were to commercialize it, you need to pay a fee to commercialize it, and that's going to be a problem. And even in the industry, people would think twice before using the work from academia because of this licensing issues. So that's something we had to um, manage. Also the data quality, because if the data is not that good, especially the resolution, it's very difficult to identify the litter. So we had to make sure we had good smartphone cameras to capture the device, so the image. And finally, on the updated data architecture. So you have seen RoboFlow doing well with the capturing all the litter, just like Euro. But the problem was the recall was not that good. It was not capturing all the litter on the street, like most of the litter. And even if it does, the precision was not in an acceptable range. We are still working on the data quality and increasing the data set size, but we found a better way to do this. This is the parallel approach that we are trying right now. So we are training a primary model like RF Beater. It's a very heavy model. So it can pick up most of the litter. So we have cut down from 8 categories to just 2 categories, just litter and refuse. So the model is doing really well now. It's picking up all the litter on the street. So it's an acceptable range. Then we crop it out and use a small classifier like mobile net or tiny VIT to classify into one of these categories. So we are actually pushing the model to classify the detected object into one of these buckets. So that's actually working well. And the last couple of days, we have seen very good result compared to what we have seen in the first video. So this is something that's very promising. I just wanted to bring it up because sometimes you don't have to do all of this in one shot. You can do hierarchically, so it can scale as well. So you can even from here you can go to plastic or you can go to paper and so on because it's not going to take much resource anyway. So that's the idea. And some of the takeaways from this talk that I wanted to give you. So if you can, always go open source first before going to some state of the art like YOLO because it can benefit a lot of community. It can benefit enterprise as well in one way. Your work will be used by people, and it always have performance par with the other enterprise models. So always try open source first. And there's no best architecture. It's not like there's a best architecture for a problem. It's about you try, you experiment, you get the feedback, then you reinvent and you adapt. But you must be always flexible to that change. Also, get the V0 ready as soon as possible. Because if you wait for the right architecture or if you wait for the right product, then you can't go live in that time scale. So you need to get a V0 ready with whatever you have and then build on top of it. And also aim for an early pilot. So we have a pilot with Glasgow City Council this December. And since we were going for an early pilot, we found they were interested in our product much more than what we expected. So that gave us more confidence because we have now more interest on our side. So always try to go for an early pilot to get the feedback from the users, the real users who are going to use it. And then you have plenty of time to work on those feedbacks and go solid onto the market. So yeah, that's the presentation. So any questions here?
Very good. Thank you very much, Bipin, for your excellent presentation. So please, we have any questions. Sorry. Oh, please.
Is it stop the recording?
Yeah, maybe.
Any questions?
Yeah. So regards to the architecture framework that we've been talking about earlier,
Sorry, which one?
the frame architecture in the slides.
Yeah.
Yeah. So comparing that with the improved one
Yes.
that you showed at the end of the slides,
Yeah.
are you going to sort of integrate both of them, or are you going to use the or that one is just the improved one that you're going to use at the end of it?
The hierarchical model, right?
Yeah.
Okay. So I'll just show that.
Slide.
So this one, yeah.
Yeah, and so this one is
I think this is very important, Bipin.
Yeah.
Please try to explain this. I just want to add maybe why maybe your concern, what is the relevance of Bipin's works to Earth observation. I hope anyone else can listen, hear me. Well, Felix and Jean. Maybe I have to get close there. Yes, I just want to add why what is the relevance of the Bipin's work to Earth observation. I think the reason is that we need to listen to AI engineers. A lot of time we don't know these models. A lot of people in remote sensing, they know YOLO or faster understanding on those models that has been used broadly in computer vision. But these models are not well known, like what is called RF detector. It's vision transformer based models. So the main objective is just to know these models that we can use it for Earth observation as well. But there are some other aspects that Bipin has brought to this meeting, like commercialization aspects that when you join industries, you cannot use, for example, YOLO because of intellectual property issues. He showcased how to, use edge devices, or maybe he's going to use, but not now, but at least he mentioning it. Because the main objective is not just to listen to very scientific works, also to know how industry works with these models and what are the challenges there. Because some of you maybe might want to join the industry instead, not to just join academia. So that's why we want to have mixture of people in this kind of meetings. Yes, back to your question. Sorry, I just want to add. Yes, please try to address this little bit, that how you can use this in remote sensing as well. We have a big remote sensing data, like covering kilometers. And just try to highlight, I mean, this is used in litter detection, just the students here can know, can be used in remote sensing and Earth observation similarly.
Yeah. So basically, your question was initially, the architecture, if you remember, we were trying to predict all the higher little categories in one pass. So that might seem like the good thing to do at first, but it's like you might miss some objects, that are that you are supposed to capture. But if you are approaching this way, sometimes even in remote sensing, like if you can capture all the objects and then you can specifically target each here. So the classifier here does the the main role of like identifying the features that separates each of these classes. So the bigger model will take care of the bulky work. So that's the idea that led to this approach and this experiment. I have been doing it for the past 3-4 days, and I have seen like tremendous improvement on the first one, where the model was struggling to actually classify it into which category. But I am trying this classifier with CNN, like MobileNet, and I also tried it with VIT, and both of the models were doing good in finding the exact features that separates the both classes. For example, if we have full litter from a drinks litter, it's very difficult for RF litter to do it initially, but the classifier was doing it really good. Because it's a cropped out version, the model has no other distractions, maybe that can be the reason.
Maybe I just want to say how it works with remote sensing. So in remote sensing, you have a big data. So I think the primary model, or I think it's called RoboFollow, right?
Yeah,
RoboFollow detector. It's vision transfer based model, I think.
Yes.
So it just discriminate litter from other items, and then second part classifier crops the whole image and then decide about the item type. We have similar thing in remote sensing as well. We don't need to process the whole image. We want to, for example, in I think Hacking presented this work of different type of targets or tanks. So maybe we just need to specify where our targets are, and then crop those targets, and then specify target size, target type. Similarly to what Bipin has developed here. Because the big data is there. We don't want to do this, use this detector everywhere, the whole image. Just focus on the specified area in the first step.
And in this way, you can also easily train the classifier, because if you want to add more data, you don't need to worry about other litter popping up in the background, because this is very focused. Your classifier will be having dedicated number of samples that you wish to have. You have full control, unlike the bigger picture that RF litter is in. So maybe that's the one of the important part that distinguishes it from the previous architecture.
For the classifier, are you using a MobileNet or?
Yes.
Okay.
I tried both CNN and the VAT, like vision transformers, but CNN was better, because I feel like you need a transformer when you have complex scene background. For example, RF reader here does good work because for example, you see a carry bag with the McDonald's packet, maybe it will make sense for the model to identify purpose later or eventually. But for a classifier, it's just seeing a cropped out part of the litter. So it doesn't require that kind of attention mechanism. It's just unnecessarily increasing the complexity. But a CNN is really good at understanding the features, like maybe the border or maybe the color of the packet or the logo can actually do a very good job in classifying. So that's why it was doing better than the previous approach.
So the attention mechanism is primarily needed in the first part.
Yes, only if the scene is convex. Otherwise, if it's just a classifier, then I don't see a reason unless we have to make sense of it in some way. But in this application, I felt CNNs are much powerful than V8. But at the same time, there was a master student who worked on brand identification for this project, and he was using MobileNet and also a vision transformer called Mobile VAT, and both of them showed good performance, but the vision transformer was doing better. Maybe it's because he was working with the logo specifically, and the I don't know, maybe the transformer might have found some way to link it to the litter, so the brand name. But yeah, that was one use case where it worked.
Any questions?
The input to this model is video, right?
Yes.
So what would the size of the video, and is it continuous feed? Like, let's say the dash cam is going to capture, let's say someone goes home, they'll be capturing for, like, let's say 30 minutes or 40 minutes will be continuously. So how is that?
So most of these models, including the RF reader or mobile nets, it can handle a lot of frames per second. But right now what we're trying to do is we'll put a limit on the mobile app. So you say you had a continuous shot for like 4 minutes or 5 minutes max, then the user will stop. So that video will be saved and processed offline. So the model takes its time to go through.
Okay.
But it's all happening offline. And the good thing about doing that is you don't need to send the entire video to the cloud to process there. Because if it's in the cloud, then you have the freedom to use all the models in the world because you have all the plenty of resources.
Right.
But on mobile, it's not the case. So also we don't want the application to get hung, or we don't need any extra bulkiness.
Right.
So I think continuous real-time detection is possible. Although it says real-time, it's not actually real-time.
Okay.
It's the model will use the saved videos, because if you do that, the user say you are not satisfied with the video. So you don't need to unnecessarily invoke the model and drain your battery. You can just delete that, and only the ones you select for processing will be processed.
Okay.
So that's another idea.
So when you say the model is running in the client's mobile phone,
Yes.
right? That will be. So do you have any specific limit on the phone, like
Yeah. So
minimum RAM or capacity?
yes. So that's a good question, because most of the time the consoles use iPhone, like the basic 6 or 7, iPhone 7 or something like that, the consoles have. And we have developed this for Android. So that's one OS difference is there. However, we made sure from the designing phase that we stick with not Java but React Native, because if you go for React Native, it's very easy to migrate to a different OS like Apple or maybe some other operating system that comes out. So we decided to like that. But coming to the specification, you need to have a GPU on your device in order to run this locally, and you need to have a good camera quality. So we have a tech specification that we agreed before giving the product to any council.
Okay.
So they need to have this in order to run this.
So the council, whoever has to install this app, need the GPU or whatever specification.
Yes.
They want to take.
The mobile device must have that. And in most cases, the smartphones these days have already this configurations. You don't need anything extra, but you just need to make sure you check all the boxes before you provide, because that can be an issue.
Okay. Got it.
Everything. So
Thank you.
yeah, we just continue the meeting. Just friendly, if you can just stop sharing. Thank you very much, Felix, for joining, and Hisham as well. Do you have any questions? Sorry, maybe program.
No, thank you. It's very interesting for us. I don't know why why not seeing me. I think I have a problem with my camera. Now sound it's